All right, so what we're looking at now then for the last thing in this unit is applications of cubic functions. All right, so we've got here our example and we'll look at working through that. Okay, so we've got a square sheet of tin, okay, and it measures 12 centimetres by 12 centimetres. 4 equal squares of edge x centimetres, okay, so that's x by x, are cut out at each corner. And the sides then are folded up to form an open rectangular box. So what we've got effectively is a box okay, an open box, and this is where a sketch helps. Okay, so when these are folded up, then we've got that dimension there is x all the way around here, which means also that our dimensions across there are going to be 12 minus x minus another x, so that's 12 minus 2x across that way, and it will be the same that way, 12 minus 2x. Okay, so that's an important thing when you're working through a problem like this, just to draw a sketch and just to put on that what relevant values, numbers, dimensions there needs to be. So that's going to help us here with part A, find the values of x for which the volume is 100 cubic centimetres. Now, how would we work out the volume of a box? Okay, we know that volume is equal to length times breadth times height. Okay, so it's going to be our length by our breadth by our height. So that's 12 minus 2x times 12 minus 2x times x. Now, we know that the volume is 100 cubic centimetres, so we need to therefore let our 12 minus 2x, this expression that we have for the volume, equal 100, and then solve for x. Okay, so if we were to do that, then we can expand that out. If we expand this, we're going to end up with, I'll just go straight to it, so fully expanding that, if you do that, you should end up with 4x cubed minus 48x squared plus 144x, okay, and that is equal to 100. And what we can do at this point here, particularly with something like this is going to be in the calculator section, there is no reason why you couldn't use your calculators to solve that. Okay, so what we can do then is we can go to our calculator and then on the keyboard, click solve, and put in what we've got here, 4x cubed minus 48x squared plus 144x, and that's equal to 100. And we can see that we've got three possible values here, 1, 3.2, and 7.8 if we round that up. Okay, so then we've got x equals, what was it again? 1, 3.2, or 7.8. Okay. What's interesting is that if we have a look at these possible values, okay, for x, we need to think, how is that actually going to work? We can certainly make it work for 1, and we can make it work for 3.2, or can we? All right, this is 12 centimeters. Halfway is going to be 6. So if we've got a value of 1 on each side, that's going to work. If it's going to be a value of 3.2, okay, then that's going to work. But 7.8, that takes us over halfway. So really what we need to do is think practically about it, and we can see that that value must be rejected because it's not going to work. Okay, so these are our possible values for x, 1 centimeter or 3.2 centimeters. Okay, part B, then we're going to look at what we've got here. Now this is an expression here for our volume. Okay, volume is equal to 4x cubed minus 48x squared plus 144x. So then let's go to our calculator. I'm going to highlight that, okay, and copy it, and then go to our menu and go to graph and table, and then paste that in because that is our equation, or it's our expression for the volume, and then we can graph. Now what we need to do is we need to zoom out so that we can see that a little better. Sometimes you might need to go zoom auto, but I think I must be getting, no, I might just save myself a bit of time and go zoom auto. And that hasn't actually worked very well, has it? So I'm just going to zoom in a little bit here. Keep zooming. Okay, we're getting there now. All right, zoom in a little bit more. Okay, so what we can see then is if we were to put here, I'm just going to put 100 there, okay, and sketch that graph. Okay, this value of volume equals 100 corresponds to these values that we've got. Okay, we can see here it occurs here at 1, here at 3.2, and then over here would have been that 7.8. Now, if we have a look at what this means here, we can see that there's going to be a 0 volume down here and also here. Over here, the graph actually becomes irrelevant. Okay, so excuse me. By graphing that on here, we can see that we've got a maximum value here, and that's what we're after, because we're after the maximum volume. So what we're going to do is just go, actually I'm just going to redraw that without that, okay, and go analysis, G-solve, and then max. What that's going to do, it's going to highlight this maximum value that we want. We can see by looking at that, with an x value of 2, that's where we've got a maximum volume, and the y value here of 128, or in this case it's V, isn't it? So it's volume. So what we're going to do, okay, max volume is going to be 128 cubic centimeters, which we can see from graph. Okay, and might be worthwhile writing down here when x equals 2 centimeters. Okay, so typically with our applications, we often will find that we use our graphics calculator to help. Just makes it a little bit quicker to work through the solutions as well. Of course, it doesn't have to be done using the graphics calculator, but it certainly saves time.